So carbonate was one we looked at the other day. That's CO3, 2 negative. Sulfate is one we see a lot. What's that one? SO4, negative 2. Okay, so because these have negative 2 charges, when we turn them into acids, we can add 2 hydrogens to do that. But if we only add 1 hydrogen, it's still ionic. So when we add 1 hydrogen, HCO3, we can either call that bicarbonate or hydrogen carbonate. So this could be hydrogen sulfate or bisulfate. How does that affect the charge? Is it still going to be a negative 2 or is it going to change? It's going to change. So remember we had noticed that when we have a hydrogen added to the ammonia, that made the charge go up to +1. So hydrogens have a +1 charge. So this one's going to be 1 minus. Okay, we change the value of the charge by 1. So adding hydrogen is the only way that we change an ion to just the charge. When we add the oxygens, the charges still stay the same. We just change the name. Okay, so our hydrogen sulfate is HSO4, and then it's 1 minus. Okay. So on your bold ions, I've given you carbonate before, I've given you sulfate before, but I haven't given you hydrogen carbonate or hydrogen sulfate. I usually say hydrogen sulfate, but because baking soda is always listed as bicarbonate, it is just ingrained in my head that that's bicarbonate. But you can call it either one is appropriate. If I give you the name, I will try to give you both versions. I will say bicarbonate or hydrogen carbonate, same formula, and ask you what the formula is, okay? Some of those polyatomic ions and acids might show up on your quiz. If I did turn these into complete acids, H2CO3 and SO4, what's the name here?
Carbonic acid.
Carbonic acid. So we change the 8 to ic. So this becomes sulfuric acid. So sulfur and phosphorus do this weird thing where they keep their whole name rather than just changing the ending. So this was sulfate. We don't have the whole sulfur in it, but when it's an acid, it's sulfuric acid. Same thing with phosphate, becomes not phosphic acid, but phosphoric acid. I don't know why they do that, but they do. Okay, so aside from naming acids and polyatomic ions that are bold on our polyatomic ion sheet, what else is going to be on the quiz? Okay, so yes, other ions, but balancing. So that's the kind of thing I was looking for. So balancing equations and then the molarity stuff. Now, I think what I'm going to do is I am going to let you work together on a combustion analysis problem and have that be like a small portion of the quiz. So you'll have the opportunity to consult with other people on that. So we will go through an example of that as we get towards the end of class. So if we're still doing molarity stuff when we have only 10 minutes left, we'll switch gears. But I want to get back to the molarity. We had, and as far as announcements goes, everything's the same. I pushed everything off to Sunday, quizzes Monday, that kind of thing. Okay, we had finished off with dilution, but we really didn't have much time to think much about it. We just sort of introduced the formula and said, yeah, we can use this. So let's look some more at dilution. Where'd the eraser go? Seriously? Steals erasers. All right, so dilution. We have a particular equation for dilution. MCVC equals MDVD. Now, these could be ones and twos, they could be initial and final. What we label it doesn't really matter. So you can see the equation in a couple of different ways. I think your book does C instead of molarity, meaning that it could be any concentration, but we're just dealing with molarity, so we're going to stick with the M. So the C, remember, stands for the concentrated, and the D stands for dilute. So I know that's teeny tiny writing. It just says concentrated and dilute as a reminder. Okay, so let's take an example problem. So Ms. Loxley is the person who prepares all of the materials for our labs. And there are 100 people, over 100 people in the lab. So even if you're only using a few milliliters of something, she may have to prepare several liters of it. So in this example, Ms. Loxley must prepare 2.5 liters of 0.15 molar HNO3, which goes by the name starts with an H, so it's an acid.
Hydrogen.
Don't need the hydro because there's oxygen. So just nitric acid. So nitric acid. Thank you for participating. Okay. And then we call this a stock solution. So whenever you see the word stock, that means that's the concentrated version. So we want to know how much of that stock solution she needs to use. So what I find helpful is to look at this equation and see what do I have the information for. So on a test, I might say, draw arrows. This one here, the 0.15, well, that's what I'm preparing. So that's the dilute. This is the volume of the dilute. So I might just like dash it out to the side. I don't really have room there. So I'm going to put the molarity of my concentrated. I know that. Oops, I forgot to tell you. I skipped a line. Okay. From 15 molar stock solution. Definitely need that information. Okay, so the molarity of the concentrated is 15 molar. The volume of the concentrated, well, that's the how much that we're looking for. The molarity of the dilute is the 0.15 molar. And the volume of the dilute is the 2.5 liters. So now that I know which things go in which place, I can just plug the things in. So using my rules of algebra, then I'm going to say, okay, I've got to divide both sides by what? Am I going to divide by my 15 molar, or am I going to divide by both of these things? The 15 molar, because I want to get this volume by itself. So I do unto one side as I do unto the other. And so I end up with that volume, plug all of that stuff in. 0.025 liters. So it's fine with me if you stop there. And this is a great final answer. But Miss Loxley doesn't have a container that is labeled in decimals of liters. She has containers that are labeled in milliliters. So what if she wanted to know how many milliliters she needed? What would she do?
You would multiply, or you multiply that by 100.
Okay, so is it going to be 100 or 1,000?
So,
1,000, because milli is 1,000. A millennium is 1,000 years, so milli means 1,000. And then let's check to make sure it's multiplied. So we have the liters on top. We want to get rid of liters and go to milliliters. And there are 1,000 milliliters in 1 liter. So yes, we do in fact multiply. And so that would be 25 milliliters. So unless I specifically say in the problem, find this in milliliters, which I usually forget to do, so you usually don't have to, you can just stop at liters. Okay, that is the correct volume. But I would anticipate on your next test having questions where I say, what is 0.025 liters in milliliters? So you're going to need to know how to do that conversion. Okay, so let's try another example problem. Let's say that we only have a small amount of H2SO4 stock solution available, and we want to know how much of the diluted solution we can make. So our question is, what volume of, what was my concentration? 0.3 molar. What's the name of that acid? This one was nitric. That one doesn't have nitrogen in it, so it's sulfuric. Okay, good memory though. Can be made from 150 milliliters. Of 18 molar stock solution. Okay, so stock solution is just the solution we have sitting in the stock room that is more concentrated, and we can dilute it to make the other things. All right, so take a second to figure out which of these things do you know. Okay, is that what you determined? And then we're going to plug that into our formula, MCVC equal MDVD. I'm going to write this out, moles per liter. That's okay. So why did I put this extra space for this conversion factor in here? Yeah, I need to turn this into liters because liters and milliliters aren't going to cancel on their own. So I want to cancel liters, which is on the top. So I'm going to put it on the bottom. And the liters here is on the bottom, so I'm gonna put liters on the top. So 1,000 milliliters per 1 liter. I think somewhere in there I said liters when I meant milliliters. So if you got confused, sorry. All right, so our volume, somebody is telling us at 1.5, I got a different number.
Oh, you will.
Okay, so this turns out to be 0.15 liters. That is correct, but our final answer is not 0.15.
No.
It's all right, Xander, do you have an answer? You kind of look like you're half raising your hand.
No,
No.
my head's very itchy.
Okay. Just fall out. All right, anybody brave enough to venture an answer? It's a nice number. Good number for a baseball team. That's a bit large for a baseball team. All right, so our 18 times our 150 divided by 1,000 gives us 2.7. Right? So, and this is moles, because the liters cancel and the milliliters cancel. This is moles. Okay, and then we're going to divide by the 30 moles per liter. So it's going to be divided by 0.30 moles. And dividing by a fraction is multiplying by the reciprocal. So the liters goes up here, moles per liter. So the moles cancel, we end up with liters. What's 2.7 divided by 0.3? 9. That's why it's good for a baseball team. Of course, that leaves you with no backups, but at least you don't have to forfeit.
Mark off if we did show the conversion from milliliters to liters?
No.
Okay, so
So if you happen to look at this and you can just instantly say, oh, that's 0.15 liters and wrote 0.15 liters, that's fine.
okay.
If you don't show your work at all and you get the right answer, generally you're going to get credit for that. There are a few types of problems, like if I'm asking for the empirical formula, I need to see the work, but like this type of problem, if you got the right answer, okay. But if you get the wrong answer and you don't show your work, I can't give you partial credit. It's just all
I
that.
just want to make sure I didn't have to show it.
Okay, 9 is a whole number. How many sick cakes do I get? I got 2 here, I got 2 here, 2 here, 2 here, 2 here. This looks like 1, but when I change within the metric system, it's infinite, okay? So this is 9.0 liters. That should probably be more than enough for our labs. Okay, so those are dilution problems. Now I want to look at going back to finding either molarity or numbers of moles. So the first thing I want to do is look at a problem that is similar to what we did on Wednesday. So similar, we're going to still use one of the same beverages. So we still have our bottle of Frappuccino. Dilution what? Yes, anything involving molarity is on the quiz. So, two things we might be interested in. We might be interested in how many moles of caffeine there are, if we were just gonna use this bottle and react that caffeine somehow. Or we might be interested in the concentration of the caffeine. Okay, so in order to find moles, if we are given the mass, then the mass is talking about a pure compound, and we can use molar weight, right? So we don't have to worry about this being a solution if we know the mass of that chemical, all right? So the only problem I see is that our mass is in milligrams. And so far we've worked with our mass in what? Grams. Okay, so we need to change this to grams. I'm going to put milligrams on the bottom, grams on the top. Where's the 1,000 going to go? On the bottom. So it goes with that M. All right, so now those are pretty units. And then we're going to have to use what? Need another number to do something with, but that's really the only number in our problem. Well, I guess we have the milliliters, but that's not going to help us. 1 is a good number to use sometimes, but in this case, we want to go to moles, so we need something that has mass and moles, grams per moles. What is in grams per moles? Molar weight. So if you look back to your notes from Wednesday, we said the first step in this kind of a problem is to find the molar weight. So we're going to look at this, C8H8N4, sorry, that's sloppy 4 there, 4O2. All right, so take a second to find that molar weight. All right, anybody have the molar weight? Xander? That is exactly what I got. So the molar weight of C8H8N4O2 is equal to 194.192 grams per mole. If you don't remember how to do that, that's something to really work on, because we're going to be using this throughout the semester. So we're adding up the mass of 8 carbons, the mass of 8 hydrogens, 4 nitrogens, and 2 oxygens. Okay, so I'm going to go from my grams over there. That is my measured amount. It tells me how much is there. So that's why I start with that one and not the ratio. This is a ratio because it has 2 units. 0.075 grams times my ratio with moles on top and grams on bottom. The number goes where grams goes because that's the first unit. And let's see, what did I get? So your calculator might spit this out as a decimal, or it might spit it out in scientific notation. So I'm going to write it both ways. Sure, I have that right. So in scientific notation, this is going to look like 3.9 times 10 to the, and then I count how far I have to move my decimal. 1, 2, 3, 4. So this is 10 to the -4. Okay, so either way. Now on your calculator, especially the smaller calculators, they don't really have room to write that all out and have like the exponent. So it may appear on your calculator, instead of 3.9 times 10 to the negative 4, it may appear as 3.9 capital letter E negative 4. So if you see something like that, that means in scientific notation with the exponent of negative 4. Okay, so have we done the first part? Yes, we found moles. Done. Okay, so now the second part says we are going to find the concentration. So this one is just plugging into our formula for molarity. So what is molarity equal to? Moles over liters. So the concentration is going to be 3.9 times 10 to the negative 4 divided by my 281 milliliters, but I need to convert that. So 281 milliliters times 1 liter over 1,000 milliliters is equal to 0.281. 0.281 liters. Okay. And what does that give you when you plug that in? 0.0014 mole per liter. I think that's what I got. Double check. Yep. And this would be 1.4 times 10 to the negative 3, because that would involve 1, 2, 3. So if your calculator said 1.4 E negative 3, that means the same thing. Okay. So we've looked at finding the moles, finding the molarity. You may ask to do things in slightly different orders. So let me see. Yeah, I've got about 7 minutes. I can do this. For example, in a few weeks, if you have lab, you'll be doing a titration. That involves those burettes where you have to like read the number, then drain it and read it again. So let's try this problem. A titration of 0.1844 molar NaOH uses 21.85 milliliters. How many moles is this? So now instead of finding moles from the mass, we don't know what the mass of NaOH is, we have to use the concentration. So we're going to remember that molarity is equal to moles over the volume in liters. So moles is equal to what? How do we rearrange this to solve for the letter N? Molarity times volume. Okay, so give that a try. All right, so what did you get for the number of moles? Should be a pretty small number. Nobody's brave enough to venture a guess.
0.004.
That sounds like what I got, 0.004. Now I should have 4 sig figs, so you said 029, and that is what I got. Okay, but my calculator didn't say that. My calculator had 4.029. And then on these little calculators, they do it a little bit differently. They just have the -3 up here. So that doesn't really mean this to the power of -3. This means times 10 to the -3. Okay, so if you see a little calculator, the ones that don't have the graphing thing on it, do it this way. That's what it's doing. Okay, let's try this one. This is going in a different direction. We've had the mass before. Now we're looking for the mass. So we use potassium iodide in an experiment or a demonstration called elephant toothpaste. So if I want a 6 molar solution of this potassium iodide and I need 250 milliliters, then what mass am I required to form? So let's try using unit analysis to solve this. I'm looking for mass. The amount I have is 250 milliliters. So I'm going to start with that. And I know that everything in molarity involves liters, not milliliters. So I'm going to go ahead and change this to liters. Okay. And if I'm going to find the mass of this potassium iodide, I'm definitely going to need to know how many moles I have. So fortunately, molarity has both liters, which is the units I have now, and moles. So let's get rid of the liters and go to moles. 6.0 per 1 liter. And then I want to go to mass. So I'm going to need to know something about potassium iodide. What am I going to need to know? The molar mass. Okay, so potassium is 39.1 and iodine is 126.9. So it kind of looks like a whole number when you write it out, but it's not really a whole number. It's 166.00. We're not really losing any sig figs there. Okay, and that's per 1 mole. So when I have a whole bunch of these conversion factors, I multiply across the top and divide across the bottom. So I'm going to plug in 250, I'm going to skip the ones, times 6 times 166 divided by 1,000. And when I do that, you got 251, I got 249, and that's probably a matter of where we rounded things. Oops, not 9. And I want to make sure I have the right units. So my milliliters cancel, my liters cancel, my moles cancel, and I'm left with grams. Okay. All right, so before we go and do the combustion analysis problem, I want to take a look at this diagram in the back that I drew. So we have several things that involve ratios. We didn't talk much about density in here, but you probably, if you had lab, talked about density. So that is mass divided by volume. And then we have molar mass, which is mass divided by moles. And then we've just introduced molarity, which is moles divided by volume. So this may help you, it may not help you, but if it does, great. Okay, so the things that are circled are a mass. These are things that you might start your calculations with. They would go into your calculator first. So mass tells me how much is there, volume tells me how much is there, moles tells me how much is there. Now, when I do division in fraction form, the top number goes in the calculator first, and then I divide by what's lower. So the way this diagram is drawn, it shows you which one is higher. So when I do density, it's mass divided by volume. Mass is higher than volume here. When I do molar mass, it is mass divided by moles, because moles is lower down than mass. When I do molarity, it is moles divided by volume. Okay. And then, so I've got those little calculations in there. And then I have arrows showing you if you want to go from moles over to mass, you're going to multiply these two. If I want to go from mass over to moles, I'm going to divide those two. Okay. If I want to go from mass to volume, I am going to say mass divided by density. But if I'm going from volume to mass, then I multiply volume times density. Okay, so that's how this diagram can kind of illustrate for you what to do in various situations. So the key thing is to remember which of those things do you need. So am I looking for moles? Well, how am I going to get there? So a question might say, how many moles? Did you start with a mass, in which case you're going to go this way? Or did you start with a solution? You have the volume of the solution, in which case you're going to go this way. Okay. All right, so let's take a look at a combustion analysis problem. So this is going back to our empirical formulas. Whenever you have a problem, whether it's combustion analysis or not, it might be a percent mass, might be something else. Whenever you have something that says find the empirical formula, your thought bubble should be translating this to divide by smallest moles. So I hear empirical formula, I'm thinking this is where I got to find moles of everything and then divide them all by the smallest number, okay? So in a combustion analysis problem, we have a compound. This one has oxygen in it, CHO plus oxygen to burn it. That's how we get combustion. And it's going to form carbon dioxide and water. So the numbers I'm putting down here are the given numbers in the problem. I didn't leave myself room to write this. But our problem is we burned a particular compound and we ended up with, where am I? Oh, next page. 24.6 grams of carbon dioxide and 12.59 grams of water. And then magical fairies came and told us the number of moles of oxygen because it just takes a really long time to go through that whole process. So I'm just going to tell you, we also know we have 0.1397 moles of oxygen. Okay, so all of this is what the information that is given to you in the problem. So none of these numbers are numbers you would have to come up with something. Okay, and then the question would be, what is the empirical formula of this compound? Okay, so we are going to have to get to moles of each of these elements: the oxygen, the hydrogen, and the carbon. So we know the oxygen is the 0.1397. Now the carbon, all of the carbon in here turned into carbon dioxide. can I figure out how many moles of carbon dioxide I have? Yeah. So what am I gonna need? Molar weight. So if we look at our chart back there, in order to find the moles, I need to take the mass divided by the molar weight. So my molar weight here, 12 plus 16 plus 16, 44.01 grams per mole. And we're going to do water too, so that's 18.02 grams per mole. Okay, so 24.6 grams of carbon dioxide times 1 mole of carbon dioxide divided by 44.01 grams of carbon dioxide times 1 mole of carbon over 1 mole of carbon dioxide gives me, oops, I didn't do the calculation, 24.6 divided by 44.01, 0.5590 moles of carbon. I'm going to do the same thing for my hydrogen. So all of this hydrogen ended up in the water, and I started off with 12.59 grams of water. But I don't want water, I want hydrogen, right? And every molecule of hydrogen or water has 2 moles of hydrogen. So I need to double the number of moles of water in order to find the moles of hydrogen. So 2 moles of hydrogen per 1 mole of H2O. And that's going to give me 0. That 12.59 divided by 18.02 times 2. There it goes. 1.397. That's 4 sig figs moles of hydrogen. And then I also know I have this 0.1397 moles of oxygen. So going back to the original question, empirical formula means divide by the smallest number of moles. So which element am I going to use those moles to divide by? Oxygen. So I'm going to divide here. 0.1397. I can do that in my head. That gives me 1. Here, 0.1397. Those are like exactly the same thing, but off by a factor of 10. And then I divide here, 0.1397. That one I have to do in a calculator. 0.5590 by 0.1397. And I get. So if I answered the question, not quite. I've gotten ratios, but I haven't actually written the formula. So my formula is C4H10O1. So I'm just gonna invisible one that. Okay. I will not put oxygen on your quiz. It'll just be hydrogen and carbon. I just get tired of doing the same ratios. So I always say, when in doubt, find moles, because that's usually the first step to any of these problems. All right, I will see you all on Monday. I will be in my office a little bit this afternoon if anybody wanted to stop by and ask any questions before then.
Can you repeat that, please? Sorry.
I will be in my office a little bit this afternoon. I'll probably be here until 4, so.
Okay.
Hand in your test and the